So we're going to try and establish a better pattern or a formula that will allow us to use summation to calculate the area or to estimate the area under the curve in a way that uses summation but is therefore much easier to calculate. So I'm going to start with this idea, that the area of the region is being estimated by the sum of the areas of a series of rectangles. How many rectangles? Well, how it changes. We did it for a single rectangle, we did it for 2 rectangles, we did it for 4. Eventually we would like to be able to go to larger numbers than that because, as we saw, the estimate of the area got better and better the more rectangles we used. Now I'm going to take this a step further and say that for each rectangle, the area was the height of that particular rectangle times the width. Now, recall that we saw that the width was the same for every single rectangle as long as we choose to make it that way, which I can't imagine why we would do any other way. It would certainly make our lives more difficult. Of course, the question is, what is that width? Because it was consistent for every rectangle when we had 2 rectangles, and it was consistent for every rectangle when we had 4 rectangles, but it was a different value each time. Well, the reason is that we're taking the total width of the interval and splitting it up into smaller and smaller pieces. So that's the first part, that the width when we use n rectangles is the total width of the interval divided by n rectangles. That should, I hope, make sense. I mean, we want to take the total width and split it evenly into however many rectangles it is we're using. Now, that actually has a better formula, which we will get to shortly. Now, the height of the rectangles, well, that's a little bit more complicated because it will involve evaluating the function at a different x value for each rectangle. So let's start with this. H sub I is the height of the ith rectangle which is the output value of the function at the right endpoint of the ith subinterval. Okay. Unfortunately, that's not quite as straightforward as the formula for the width. This is going to require a little bit more finagling, a little bit more care. So, let's try this. Now, the interval that we're using is different from one problem to the next. So the example in the previous video was on the interval from 0 to 2. It could easily have been an interval from 0 to 5, or from 1 to 8, or from -3 to +2, or any other interval you can imagine. So for each function, for each situation, the interval is different. So I'm going to say that the interval in general should be called A to B. Now, what I'm going to do is draw out a portion of the number line whose left endpoint is A and whose right endpoint is B. Now, we're going to subdivide it into n intervals. Now, I use the ... because, well, there are any number of intervals in there, so, you know, I don't want to lock us into a very specific number at this time. Now, I'm going to do something else here. I'm going to label each of those tick marks in between. And I'm going to do it with an X that is subscripted. So I'm going to start down here at A. I'm going to call that X sub 0. That makes this X sub 1, X sub 2, X sub 3, and so on. The idea is that the right endpoint of the first interval is X sub 1. The right endpoint of the second interval is X sub 2. The right endpoint of the third is X sub 3. In general, the right endpoint of the ith subinterval is X sub I. So the last subinterval, if there are n of them, the last subinterval should have a right endpoint of X sub n because it is the nth subinterval. That would make this X sub n minus 1. Now, the idea is then that if we set up our subintervals in such a way, then the output value at the right endpoint of the first subinterval would be f of x sub I, or f of x sub 1 rather. On the second subinterval, f of x sub 2. On the third interval, f of x sub 3, and so on down the line. Now, the only one we don't have an f of is this, because that's not a right endpoint. X sub 1 is a right endpoint. When we move on, x sub 2 is a right endpoint. X sub 3 is a right endpoint. And so on down the line. So what we get then is that under this subdivision, the height of the ith rectangle is f of x sub I. Of course, we're not quite done yet, because that's only helpful if we have an actual value for it. If you recall, when we did the 4 rectangles, we needed to actually know what that value was to be able to put it into the function and evaluate it. So is there a way to figure out what this value is, and this value, and this value, and so on down the line, so that we can actually put these into the function? Well, absolutely. The trick is to realize that we know the distance between these things. That distance is W. It has to be. W is the width of each subinterval, the width of each rectangle. Which means this distance is also W. And this distance is also W. And so on down the line. So an interesting thing happens here. We can find any of these values by starting at the beginning and going a distance of w that many times. So if it's the third subinterval we're looking at, and I want the right endpoint of the third subinterval, I can start at the left endpoint of my interval and go the distance of w once, twice, 3 times to get to the right endpoint of the third subinterval. In general, we could say this, that the value of x sub I comes from starting at the left endpoint of the interval and going a distance of w I times. So that when x is 1, we start here and go a distance of w once. If x is 3, we start at the beginning and go a distance of w 1, 2, 3 times. And so on. Now, I'm going to come back to w for a quick moment. Now that we have this interval a to b, and say that the total width of the interval can be found by subtracting b minus a and dividing by n. We're also going to give this a new name because, okay, we are only looking at a horizontal number line, but this is reminiscent of something that you would have seen before, slope. Slope of a line where we go up and over, rise and run. Every time we do that, the rise and the run are the same. Okay, well in this case we're only looking at the one axis, so we're only interested in the run, but the idea is the same, that we're always moving, we're always stepping by the exact same amount all the way down the line. In slope, we call that delta x. Delta is a Greek letter, and it is used in mathematics to represent change in a variable. So literally the amount that x changes by. So, conclusion statement. The area of an irregularly shaped region can be approximated by adding up the areas of n rectangles whose areas are calculated by the height times the width, where the height is the output value at the right endpoint of the ith subinterval times delta x, where delta x and x sub I are given by these two formulas here. This is called a right endpoint Riemann sum. Now, this is very much keyed into the idea of using the right endpoint so that the subscript on x matches the subinterval that we're talking about. So when we're talking about the first subinterval, x sub 1 is the right endpoint. On the second subinterval, x sub 2 is the right endpoint. And that tends to work out very, very well for summation. It helps that we have our summation starting at 1 for our indexing variable, so that we can use the properties and the formulas freely when we eventually get to the point where we do that. A left endpoint Riemann sum or a midpoint Riemann sum. Remember, those are the other two options that I showed you for determining the height of the rectangles. Those are a little bit more complicated. We will come back and take a look at how to do those later on. But they are more complicated because they include either starting at the left endpoint, which means for our first subinterval we want x sub 0. That mismatch of subscript to interval kind of gets a little bit hairy. If we want to do the midpoint, we'd actually have to calculate what the center of that little subinterval is. So not the best choices if you're looking for ease of calculation. So right endpoint Riemann sum. This in general is a Riemann sum, named after the German mathematician Riemann, who developed it. This part is true. The delta x is true no matter what endpoints we're using, left, midpoint, or right endpoint. But this formula here makes it a right endpoint Riemann sum. So we now have a structure by which we can calculate the area a little bit more efficiently. So in our next video, we're going to take this and we're going to go back to our area with 4 rectangles and use this and verify that we get the same results.